particularly what it means for them to be injective and surjective. Last time we talked about a particular injective and surjective linear map. And today I want to zoom in on that situation and talk about invertibility of linear maps. So we have two vector spaces V and W. We consider a linear map F between them. In particular, F is a map of sets, right? It maps every point of this to a point of that. And we know that for set maps, sometimes, but not always, if they're injective and surjective, certainly, there's an inverse. And so we'd like to know when is there an inverse? G. So G would be a linear map from W to V such that F composed with G, so F composed with G will be a map from V to itself. We'd like to know when is that F composed with G, when does there exist a G such that F composed with G is the identity on V, and G composed with F, which is a map from W to itself, is the identity on W. This map G, if it exists, is called the inverse of F. And in this case, we say that F is invertible. So the F is an invertible linear map. So the first thing to observe is that if such an inverse exists, it is unique. Why is that? Well, suppose we have two maps, G, G prime, that go in the opposite direction. And both of these maps, G and G prime, are inverses for F. Well, I can take this map G, which is in L of a linear map from W to V. I can precompose it by first using the identity on W. That doesn't change what it is. Right. G is equal to G composed with the identity on W. And I'm omitting the little composition circles, more or less, from now on. We usually don't write them when we're multiplying with linear transformations. So G, I can always compose on the right-hand side with the identity on W and get the same thing. But by definition of inverse, identity on W can be obtained by either GF or G prime. Maybe I went the wrong direction there. Of F. So this is equal to G FG prime. And that's equal to the identity on V of G prime, changing the parentheses, GF. And that's equal to G prime. So those things are unique. And so it's okay the inverse, if it exists by F inverse. Yeah, I had these wrong, right? That's why this should have been that. Because first applying F and then applying G it gets me back here. So these were incorrect. That should be GV, GF, and this should be FG. And then these two things match. OK, so if it exists, it is unique. And we talked last time about a particular bijective linear map. And as you might guess, invertibility coincides with it being injective and surjective. A linear map is invertible in this sense if and only if it is injective and surjective. So let's prove both directions. So first, let's suppose that it's invertible. And we'd like to prove that it's injective and surjective. So for injective, we have basically two ways of proving something's injective. We can prove its null space is 0, or we can directly test by taking two vectors in V, applying F, and seeing whether or not they become equal. So suppose we have two vectors in V such that when F is applied, they're equal. And we'd like to show that the vectors must have been equal to begin with. Well, I can write U is F inverse F of U. A definition of inverse. It's equal to F inverse F of V. That's equal to V, because F of U and F of V are equal, right? This is 1, this is 1. Okay. For surjective, we need to show that surjective, we need to show that for any element in the codomain of F, suppose W is in F, we need to find something in its preimage. Well, F inverse of W is the obvious candidate. This is defined because F inverse is a function. And F applied to this vector in V, of course, is equal to W. So that shows that there exists a vector in V such that when F is applied to it, I get a thing in the codomain. I mean, there's almost nothing to show for this, really. Okay. For the other direction, we suppose that F is both injective and surjective. We need to show that it's invertible. So let's let W be an element of W. And what we want to do, the approach here is going to be kind of a guess and check approach. That is, we're going to take a guess at something that that has to be the inverse, and then we have to show that it satisfies the properties we expect of an inverse, and that it's in fact a linear transformation, not just a set function. So first consider the set of all V, all vectors V in V for a fixed W such that F of V is equal to W. So this set is the preimage of W according to F. In general, this is a set. In fact, it's a subspace. But I would argue that in in this case, if f is both injective and surjective, in fact, the set has only one element. So why is that? Suppose it has two elements, v and v prime. F of v equals f of v prime equals w, because that's what this set is the stuff that maps to w. But then because f is injective, these two things have to be equal. Okay? So this set has only one element. Since f is injective. As a result, it makes sense to define a new function, just a set function, which for every element w in big W is just this v. The v such that f of v equals w. In general, I couldn't do that because that would be a whole space, a whole set of things. But because I know it's only one vector in the preimage, it's OK to make that definition. So this is a definition of a function. It's a little bit of a backwards definition, but it's a definition. It tells me which element to pick. And this is our guess. I mean, this is what the inverse has to be. And so we have to show that this G satisfies what we want, satisfies the equations defining the notion of inverse. That is, if I compose F with G, I get the identity on W. And if I compose G with F, I get the identity on V. Well, you could work that out by just writing down something like just changing the parentheses. So look at that. It's equal to FG FV equal to the identity on W FV equals F of V. And since F is injective, so GFV equals V, i.e. GF equals identity V. But you know, just thinking about what this definition means is going to force that to be true. You can also do it by working out what's happening symbolically. Okay. So this is our set function. It satisfies the equations we would expect for an identity function. And the only thing that remains to show is that it's linear, right? So the way we defined it, we didn't talk about what it does to a basis or anything like that. And so we just have to make sure that this weird definition gives a linear function. G from W to V is, in fact, linear. That's what we need to do now. Okay, so to check it's linear, we want to check that it respects addition and it respects scalar multiplication. So suppose I have two vectors, W1 and W2, in W rather. Then f of G of W1 plus G. So we're going to use the properties of G and f to prove linearity. Okay, we'd like addition to commute with the application of G. So take G of W1 and G of W2, add them together and apply f to them. F is linear. So I can push f through to get FGW1 plus FGW2. But G and F are inverse as set functions by our definition of G. So that's equal to W1 plus W2 by the definition of G. What does that tell me? It tells me that this thing here, G of W1 plus G of W2, is the preimage the only vector in the preimage of W1 plus W2. So it must be that G of W1 plus W2 is equal to G W1 plus G of W2 by definition of G in terms of this preimage. And then we do something similar for scalar multiplication. So suppose I have A and F, and I have W in big W. I can think about F of AGW equals AF of GW, which equals AFG of W, which, because that's the identity, is AW. And that tells me that AGW is mapped to AW by F. And so it must be, by definition, that G of AW by definition of G, G of AW is its preimage AGW. And that tells me that, as I wanted, I can move scalar multiplication around. Okay. That's a bit weird, right? So I mean, we're really arguing by logic rather than by kind of directly checking. Fair enough. Okay, so we've said that linear transformations are the structure-preserving maps for vector spaces, right? And we have various words for that. So there's this word homomorphism, from which the notation that I mentioned, like that, which means the same as linear maps from V to W, implicitly we're saying, homomorphism is like same shape, so same form, right? We're saying that it's a thing which preserves the form. And we want to talk about other types of morphisms. We mentioned endomorphisms. So endomorphisms, endo means it folds in on itself. So that's maps from a vector space to itself. And so people sometimes drop because they want to have different prefixes. Over time, we've sort of just started calling these morphisms. And there's another kind of morphism, which is probably the most important prefix to remember, which is an isomorphism. Isomorphism is sort of even more the same, I guess. And this is a structure-preserving map that really makes two spaces the same. So definition, an isomorphism of vector spaces is a linear transformation, so a structure-preserving map which is invertible. So we defined a moment ago. Okay. So in particular, it's surjective and injective. Equivalently, it's surjective and injective. And you should think about that as an isomorphism is a linear transformation which in some sense makes two vector spaces the same, or tells you how to identify one with the other. Now, that's not to say that there's only one way to identify them. Right? So there may be many ways to identify them. So the isomorphism we talked about last time was that the space of linear transformations is isomorphic by this map taking the matrix with respect to a basis B and a basis C to the space of matrices, which are n by m. So this is dimension m, n, and dimension m. Right? But the point is that if I chose a different basis, I would get a different bijective linear map, a different isomorphism. So an isomorphism makes two things the same, but not necessarily in any kind of canonical way. Right? So the last thing I think I want to talk about is some propositions. Of course, there's a lot of structure for vector spaces and linear transformations, and so invertibility has many characterizations, especially in the case of endomorphisms. So suppose V is finite dimensional vector space, and consider a map, a linear map from V to V. So we also write L of V or endomorphisms of V. Then the following are equivalent. A, that F is invertible, so F is an isomorphism, V to itself. B, F is injective. And C, F is surjective. So what's surprising in a sense about this proposition is that only one of these conditions is necessary for invertibility. So the theorem we just proved was that both conditions, injective and surjective, are together equivalent to invertible. But in fact, you only need one of these in the case of linear transformations from a vector space to itself. And that's the surprising part. Okay. So by that previous theorem, we have that A implies B and C. Right? And also B and C imply A. If I have something which is injective and surjective, then it's invertible. If I have something invertible that's injective and surjective. And so the surprising thing is that B implies C and C implies B. But that's the content of this proposition. So let's suppose that B holds, that is, F is injective. The other characterization of injectivity is in terms of the null space. That is that the null space of F is the zero vector space. F is injective. And by the theorem we just reviewed, the rank nullity theorem, tells me that the dimension of the image of F is equal to the dimension of V minus the dimension of the null space of F. Since F is injective, the dimension of the null space of F is 0. So that tells me that the dimension of the image of F is equal to the dimension of V. The image of F we know is a subspace, so that means we have a subspace image of F is a subspace of V, and it has the same dimension. And that's going to force them to be equal. Different ways of seeing that. One way is to say, well, image of F has dimension, say, n. So that means it has a basis of length n. But that basis of length n is an independent set of length n sitting inside of V, an independent list. And we know that any independent list of length equal to the dimension of the space must be a basis. So that's also a basis of V. Therefore, these two things must be equal because they have the same dimension. Right? I mean, that's a special property of linear things, right? I mean, here's a set which is a subset of the blackboard, has the same dimension, but it's not equal to the blackboard. But for linear spaces, having the same dimension forces those things to be equal.